In the world of structural engineering, some of the most critical components are the ones you never see. Hidden deep within modern high-rise buildings are massive, heavily reinforced slabs known as transfer plates. These are not ordinary floors. They are structural powerhouses designed to redirect immense vertical loads from columns above to a completely different column layout below. Imagine a forest of columns supporting dozens of stories, all needing to disappear to create a grand, open-plan lobby or spacious commercial space. A transfer plate makes this architectural vision possible. The plate acts as a horizontal bridge, interrupting the vertical flow of force and redistributing it with precision. When a column from an upper floor lands on a transfer plate, its concentrated force spreads through the slab's thickness. These structures are fundamentally thick, robust concrete slabs, often several meters deep, and reinforced with a dense cage of steel bars. Think of them as giant, flat beams designed to handle loads equivalent to hundreds of tons. Designing a transfer plate is a methodical process rooted in structural mechanics. The first step is load determination. Engineers must calculate every force the plate will experience, including dead loads, live loads, and environmental forces like wind and seismic. Next, determine the support reactions using classic statics. All vertical forces must equal zero, and all moments about any point must equal zero. This calculates how much force each supporting column must resist. With loads and reactions known, analyze the internal forces within the plate. Calculate bending moments and shear forces at every point along the span. Then design steel reinforcement to resist these forces. Let's consider a simple example. A transfer plate spanning 10 meters supporting two columns from upper floors, each imposing 500 kilonewtons. These columns are placed at 3 and 7 meters from the left support. Because the loading is symmetrical, each support takes 500 kilonewtons. The maximum bending moment occurs between the two loads and equals 1,500 kilonewton meters. This dictates the reinforcement needed. For a 2-meter wide, 600 millimeter deep plate using 25 megapascals concrete and 400 megapascals steel, we need approximately 8,320 square millimeters of steel reinforcement, provided by large diameter bars spaced closely together. Transfer plate design is rigorously governed by building codes like ACI 318, which provides essential frameworks for load factors, strength calculations, and safety margins. Following these codes is not just best practice, it's a legal requirement. While simple beam theory works for preliminary design, real-world transfer plates often require finite element analysis. FEA divides the complex plate into thousands of interconnected elements, providing detailed simulation of stress and strain distribution throughout the structure. The primary benefit is immense architectural flexibility, enabling grand lobbies, expansive retail floors, and column-free parking levels below denser residential or office floors. This maximizes commercial value and unlocks a building's full potential. However, these benefits come with significant challenges. Transfer plates are incredibly heavy, requiring extensive formwork and false work. The logistics of placing tons of steel reinforcement and pouring massive concrete volumes demand meticulous planning and precision. Despite the challenges, transfer plates remain essential for modern high-rise construction, enabling the dynamic, multifunctional buildings that define our urban landscapes, proving that sometimes the strongest solutions create a sense of openness and lightness.